Hello, this video is on the theoretical subject of Gaussian primes. I'm not going to deal with particular examples, but going to rather establish a general fact about them. So a Gaussian integer is, let's start defining things, is called irreducible. If it cannot be decomposed in an interesting way into a product. So each time we have it written as a product for some two Gaussian integers, so then one of them is invertible. And we already investigated which Gaussian integers are invertible. There are just four possibilities: plus or minus 1, or plus or minus I. So up to these multiples, decompositions can be called equivalent, and then we don't have interest in non-equivalent decompositions. All of them are equivalent to basically 1 and then z itself. So we have some special properties of Gaussian integers which can allow us to say more about such irreducibles. So namely Euclid's division possibility, implies the following property, that if an irreducible Gaussian integer divides a product, then it divides one of the factors. So such irreducibles are called primes. Called Gaussian primes. And we have automatically the following statement, that any Gaussian integer is usually a real imaginary part, okay, but yeah, I'll call it that now. Any Gaussian integer is a product of primes. Moreover, well, it's kind of not a deep statement in general, but what follows is unique up to this indeterminacy, up to these invertibles, up to invertibles. So if we say that two Gaussian primes are equivalent if they differ by one of those factors, then the product of primes is, the primes in the product are unique up to this equivalence. The real goal of this little investigation is to see what can we say about such Gaussian primes, and the first thing we look at are the norms. And through the norms we're going to have a characterization of them. So let's look at, let's start with a Gaussian prime. And then what can we say about its norm? So the norm, let's assume that it's a prime. And the norm, by the definition, is a product of the prime and its conjugate. But it's easy to see that the conjugate of a Gaussian prime is also prime. Just from the very definition of what is to be reducible, which is the same as a prime in this context, if we have a decomposition, then one of the factors has to be invertible. One of the factors has to be of this form, so that taking the decomposition for the conjugate and conjugating it, we will have the decomposition for that. And we know that factors are invertible, and then they are conjugates of the factors in the decomposition of the conjugate. So let me write it down in brackets. So if I assume that there is a decomposition, then I can conjugate it and have the composition of my prime, and then know that either first factor or the second is invertible. But invertibles are closed under conjugation, so if we have an invertible number here, when we conjugate it, an invertible number is one of those. When we conjugate, we will get one of those numbers again. So then V as a double conjugate of itself, or as a conjugate of something invertible, is either invertible. So either V or E or W, which is the conjugate of its conjugate, is also invertible. And yeah, we have the conclusion. So these are the two primes we have in the multiplicative decomposition of the norm. So the norm, being an integer, that's the beauty of it, is decomposed into a product of two Gaussian primes. So what can it be as an integer? Well, I'm going to argue that there are just two possibilities. So the first possibility, it is a prime. Let me dismiss it from the start and assume that it is not. So if the norm is not a prime, then yeah, write it down as some product, some interesting product. So now A and B are integers, and they are not plus or minus 1. So I can really forbid plus or minus 1 by this synthetic construction. And then I have two decompositions, so one decomposition into the product of Z and Z conjugate, and then the decomposition into this product of A and B. So this is the decomposition in integers, this is the decomposition in Gaussian integers. They both work in Gaussian integers. But I have this convenient statement that such decompositions are unique up to invertibles. So these two have to coincide, the factors have to coincide up to these multiples of plus minus 1 plus minus I. So we can be sure that that is either equal to A or B, but yeah, we can redefine them. So we can be sure that, say, that is equal to A up to plus or minus 1 or plus or minus I, which again I can ignore by, say, absorbing it into Z. And it still gives me the an equivalent prime, so I'm not going to change my story. But if that is an integer, then its conjugate, which I used to define the norm of that, is also an integer, and it's going to be the same thing. But from this decomposition, it's going to be this B. So I have that A is equal to B, and I have it to be indecomposable, so they have to be anymore. So they have to be primes. They have to be primes in, or just the same prime A in, really the same prime in just ordinary integers. So that is if the norm of my Gaussian prime is not a prime. It has to be, then the Gaussian prime has to be an integer prime. And otherwise, the norm is a prime. So I have this dichotomy really that Gaussian prime is either of a prime norm or it is a prime in integers. So what can I say more about which prime can occur in each case? So yeah, I have, let me already write my final statement, call it a theorem. So if a Gaussian prime is either a prime in integers, or it is a Gaussian number of a prime norm. So or it is of the form a plus ib, so a Gaussian number with the norm a squared plus b squared being a prime. So in the first case, when it is just an integer prime, it should not be the same type as appear in the second case, where I have a prime in integers which can be written as a sum of two squares. So if a prime can be written as a sum of two squares, then I can imagine a Gaussian integer which will have this very norm. So whatever appears in the first possibility has to be not possible to write as a sum of two squares, just pure logic. So this be either prime, not a sum of two squares. So that is a dichotomy. Either we have a prime which is a sum of two squares, and then it stays as a prime in Gaussian integers. It is a Gaussian prime, or if an integer prime can be written as a sum of two squares, it decomposes like that into the product of two Gaussian primes. I will have to investigate which primes can be written as a sum of two squares and which can be not in a later episode, so please stay tuned. See you.